Welcome back. We're going through some steps to recreate everything that we've done. In the last video, we created some dummy data and we've got a straight line here. So now, by the workflow, we're up to building a model or picking a model. In our case, we're going to build one to suit our problem. So we've got some linear data and I've put building a PyTorch linear model here. I issued you the challenge of giving it a go. You could do exactly the same steps that we've done in build model, but I'm going to be a little bit cheeky and introduce something new here. And that is the power of torch.nn. So let's see it. What we're going to do is we're going to create a linear model by subclassing nn.module, because why? A lot of PyTorch models subclass nn module. So class linear regression, what should we call this one? Linear regression model v2, how about that? And we'll subclass nn.module. So much similar code to what we've been writing so far, or when we first created our linear regression model. And then we're going to put the standard constructor code here, def init underscore underscore, and it's going to take as an argument self, and then we're going to call super dot another underscore init underscore underscore brackets. But we're going to, instead of, if you recall above, back in the build model section, we initialized these parameters ourselves. And I've been hinting at in the past, in videos we've seen before, that oftentimes you won't necessarily initialize the parameters yourself. You'll instead initialize layers that have the parameters inbuilt in those layers. We still have to create a forward method, but what we're going to see is how we can use a torch linear layer to do these steps for us. So let's write the code and then we'll step through it. So we'll go use nn.linear, because why? We're building a linear regression model and our data is linear, and in the past our previous model has implemented the linear regression formula. So for creating the model parameters, so we can go self.linear layer equals, so this is constructing a variable that this class can use, self linear layer equals nn.linear. Remember, nn in PyTorch stands for neural network. And we have in features as one of the parameters and out features as another parameter. This means we want to take as input of size 1 and output of size 1. Where does that come from? Well, if we have a look at xtrain and ytrain, we have one value of x, maybe there's too many here, x5, we'll view the first 5. 5 and 5. So recall, we have one value of x equates to one value of y. So that means within this linear layer, we want to take as one feature, x, to output one feature, y. And we're using just one layer here. So the input and output shapes of your model, in features, out features, what data goes in and what data comes out, these values will be highly dependent on the data that you're working with. And we're going to see different data or different examples of input features and output features all throughout this course. So, but that is what's happening. We have one in feature to one out feature. Now what's happening inside nn.linear? Let's have a look. Torch nn linear. We go to the documentation. Applies a linear transformation to the incoming data. Where have we seen this before? Y equals x a t plus b. Now they're using different letters, but we've got the same formula as what's happening up here. We've got the same formula as our data. Weight times x plus bias. And then if we look up linear regression formula, once again, linear regression formula, we've got this formula here. Now, again, these letters can be replaced by whatever letters you like, but this linear layer is implementing the linear regression formula that we created in our model before. So it's essentially doing this part for us. And behind the scenes, the layer creates these parameters for us. So that's a big piece of the puzzle of PyTorch. is that, as I've said, you won't always be initializing the parameters of your model yourself. You'll generally initialize layers, and then you'll use those layers in some forward computation. So let's see how we could do that. So we've got a linear layer which takes us in features 1 and out features 1. What should we do now? Well, because we've subclassed nn.module, we need to override the forward method. So we need to tell our model what should it do as the forward computation. And in here, it's going to take itself as input, as well as x, which is conventional for the input data. And then we're just going to return here self.linear_layer x. Right, and actually we might use some typing here to say that this should be a torch tensor, and it's also going to return a torch.tensor. That's using Python's type-ins. So this is just saying, hey, x should be a torch tensor, and I'm going to return you a torch tensor because I'm going to pass x through the linear layer, which is expecting one in feature and one out feature. And it's going to, this linear transform, that's another word for it. Again, PyTorch and machine learning in general has many different names for the same thing. I would call this linear layer. I'm going to write here. Also called linear transform, probing layer, fully connected layer, dense layer in TensorFlow. So a whole bunch of different names for the same thing, but they're all implementing a linear transform. They're all implementing a version of linear regression. Y equals X, A transpose plus B. In features, out features. Wonderful. So let's see this in action. So we're going to go set the manual seed so we can get reproducibility as well. Torch.manual seed. And we're going to set model 1 equals linear regression. This is model 1 because we've already got model 0, linear regression v2, and we're going to check model 1, and we're going to check its state dictionary. State dict. There we go. What do we have inside this? Ordered dict. Has that not created anything for us? Model 1 dot state dict. Ordered dict. We haven't got anything here. Linear regression model v2. Ideally, this should be outputting a weight and a bias. Yeah, variables, weight, and bias. Let's dig through our code line by line and see what we've got wrong. Did you notice this? The init function, so the constructor had the wrong amount of underscores, so it was never actually constructing this linear layer. Troubleshooting on the fly, team. There we go. Beautiful. So we have a linear layer, and we have, it is created for us inside a weight and a bias. So effectively, we've replaced the code we wrote above for build model, initializing a weight and bias parameter with the linear layer. And you might be wondering why the values are slightly different, even though we've used the manual seed. This goes behind the scenes of how PyTorch creates its different layers. It's probably using a different form of randomness to create different types of variables. So just keep that in mind. And to see this in action, we have a conversion here. So this is what's going on. We've converted, this is our original model class, linear regression. We initialized our model parameters here. We've got a weight and a bias, but instead we've swapped this in our linear regression model v2, this should be v2, to use linear layer. And then in the forward method, we had to write the formula manually here when we initialized the parameters manually, but because of the power of torch.nn, we have just passed it through the linear layer, which is going to perform some predefined forward computation in this layer. So this style of what's going on here is how you're going to see the majority of your PyTorch deep learning models created using pre-existing layers from the torch.nn module. So if we go back into torch.nn, we have a lot of different layers here. So we have convolutional layers, pooling layers, padding layers, normalization, recurrent, transformer, linear. We're using a linear layer, dropout, etc., etc. So for all of the common layers in deep learning, because that's what neural networks are, they're layers of different mathematical transformations, PyTorch has a lot of pre-built implementations. So that's a little bit of a sneaky trick that I've done to alter our model, but we've still got basically the exact same model as we had before. So what's next? Well, it's to train this model. So let's do that in the next video.